Hey guys, we are looking at video 3 today for probability 5C, tables and tree diagrams. So the first thing I want to do is think about the last question in last lesson. We had the 3 cards and they were arranged in some way with the numbers 8, 3 and 2. And I said it's not too hard, you could just think of all the possibilities, and we worked out there were 6 different possibilities. Now I want to show you a better way. Let's say that there was, even if there was another card with a 1 on it, all of a sudden, we're going to have a lot more options. So it can be harder to think of all the different options. So today's lesson is about tree diagrams and tables, and I wanted to show you this example straight away of how much the tree diagram could help us. Let's just stick with the 8, 3 and 2 and how we could do it now with a tree diagram. And this ensures that you won't forget any kind of combination that could have possibly been. So we draw branches out like this of the 3 different options we could have. You could have an 8 first, or a 3 first, or a 2 first. If you have an 8 first, so I'm going along this branch, my possibilities are then getting a 3 next or a 2 next. But if I got the 3 first, then my possibilities are an 8 or a 2. And same as if I got 2 first, my possibilities are a 3 or an 8. Now, the next option, if I got the 8, then I got the 3. The next option is then obviously I have to get the 2 last. If I got 8, 2, then my next option is a 3. 3, 8, must be a 2. 3, 2, 8, 2, 3, 8, and 2, 8, 3. Now, let's think about what that path is. So if you follow the path along, you can see 8, 3, 2 is the possibility there. So 8, 3, 2, 8, 2, 3, 3, 8, 2, 3, 2, 8, 2, 3, 8, 2, 8, 3. And there's my 6 possibilities. So you could see that tree diagram, yes, it took us a bit longer, but it is extremely handy in the way that you were never going to forget an option. And if you had another card there and had a lot more to do, this tree diagram is obviously going to help you a lot there. So they're really good for a visual aid in probability. So in saying that, let's start the lesson. So tables and tree diagrams. We're going to start by looking at tables. Tables are handy if you have like 2 options versus another 2 options, for instance. But you'll see what I mean in a second. So the first table I have here is a table drawn up showing all the possible outcomes if you flipped 2 coins. So if it said what are all the options if you flip 2 coins, okay, you'd say, well, I could get heads, heads, tails, tails, heads, tails, or tails, heads. That's pretty easy. And see how this table just shows you that. So heads and tails is my options here, heads and tails is my option here, coin 1, coin 2, and there's my 4 options. So therefore there's 4 possible outcomes. So a table just allows you to, compare the 2 different things that are happening and see all the values. So now we're going to just be asked probability questions around the table. Now you are going to be made to create these tables yourself. So 2 coins are tossed, find the probability of rolling. I should say not rolling. I'm thinking of a dice there. Flipping. Heads and a heads. So let's think about this. All of these have the same probability of occurring, right? So getting a head is 1 out of 4. And if I want to stick to what I want you guys to do in terms of your notation, setting it out like that. So then the probability of getting the coins land on the same side. So that's tails, tails, or heads, heads. So there's 2 of them out of the total of 4, which gives me 1 in 2. So then lastly, the probability of no tails. Well, that's going to be solely just heads, heads. So pardon me, 1 in 4 is my answer there. So nice and easy. And again, having that visual aid made that question so much more easier for us to see and do. Alright, this one, very common question. it says, draw a table for rolling 2 dice, okay? And the uppermost faces are added together. So let's think about this. I want you to draw this in your book. We're going to say, okay, 2 dice are rolled. So I'm going to have 1, 2, 3, 4, 5, or 6 options for the first dice. And the second dice also has 6 options. So now do yours with a nice ruler, make it nice and straight. Here's my table for all of my options. Oops, I don't need that last one. Okay. Now, it said the uppermost faces are added. So if I get, I need one more column there. A 1 and a 1. So on first dice rolls a 1 and second dice also rolls a 1. When I add my 2 uppermost faces, I get 2. Now, if dice number 1 rolls a 2 and the other dice rolls a 1, add them together, I get a 3. The first dice rolls a 3, second dice still rolls a 1, I'm going to get 4. And then you're going to come down, keep going through. The first dice, if that rolled a 1 and the second one rolled a 2, I'm going to have 3. So all you're doing is you're adding the values and putting them together. So go ahead, fill out the rest of the table, okay? And we're adding the uppermost faces. If you miss that part, it's because the question asked you to do that. The 2 uppermost faces are added. All right, I'm going to pause and go ahead and finish this table, and I want you to do the same. And there I have it. Okay, so the biggest number I could possibly get is the 12, 6 and a 6. Now I have this visual aid, it's going to help me a lot. What's the probability that the sum is equal to 6? So I say, okay, well, where do I have in my table 6s? I have here, 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 and here. So how many options are there altogether? You could count all the boxes or just note that it's 6 by 6, so there's 36 options altogether. So the probability that I got a sum of 6 was there's 1, 2, 3, 4, 5 of them out of 36, and that won't simplify. So now the probability that I have even, okay, so let's go, okay, even, this one, this one, this one. So you can use the visual aid, or if you can see it already without using the visual aid or understand how it would work, you can go ahead and do that. But counting, you should see, yes, as we would have predicted, it's half of them. So 1 out of every 2. Or if you added all of those up, you would have found there's 18 out of 36, which simplifies to 1 in 2. And last of all, greater than 5. So we say, okay, not equal to 5, so it has to be greater than. So that is all of it from here onwards, all of those. So there's quite a lot of them. So what if I just count the ones that are 5 or smaller? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them are smaller than 5 or equal to 5. So that leaves 26 out of the 36, which simplifies to 13 out of 18. So hopefully you can see there what a difference it makes when you have a table. Okay, trees. You've already seen my example of the tree, but let's have a look at these ones. So these are best for multi-stage events. So let's have a look at this. You could do a table definitely for this question, but we're going to just focus on the tree for this one. Joan, she has 3 t-shirts. There's 1 red, 1 yellow, 1 blue, and 2 pairs of shorts. There's a shorter pair and a longer pair. So use a tree diagram to show all the options and combinations Joan has to wear if she chooses her shirts first. So the first thing I said is, okay, well, if she chooses her shirts first, she has an option of a red shirt, a yellow shirt, or a blue shirt. Then, if she chooses her shorts next, she has a choice of long or short, long or short, long or short. And there you have every single possibility. So if I write this out, she could have a red shirt and long shorts, or she could have red shirt and short shorts, yellow shirt and long shorts, yellow shirt and short shorts, blue shirt and long shorts, or blue shirt and short shorts. So there's every possible combination Joan could have in wearing those. Now everything is very clear for me. The thing is though, this time, it's not the same probability for, well actually before I say any more, let's just label the probabilities on this tree diagram. The probability she wears a red shirt, well there's one red, one yellow and one blue. So it's 1 in 3 chance, 1 in 3 that it's yellow and 1 in 3 that it's blue. And the probability that she wears she's only got one pair of short pants and one pair of long pants. So it's 1 in 2, 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 1 in 2. Now the rule is, if they said to you, find the probability that she wears a red shirt and long pants, all you have to do with tree diagrams is say, okay, well I need the probability of this occurring. All you have to do is just multiply every fraction along the path of that. So I'm going to multiply a third and a half together. And note, it's red and long shorts. What do I have? What am I mentioning? The word and. What does and mean in probability? I multiply. So that's why we are multiplying along our tree. So it's going to be 1 in 3 timesing by 1 in 2. So the probability that Joan wears a red shirt and long pants is going to be 1 in 6. Okay, so I could have also done this in a table. If you like tables better and the question didn't specify what you had to do, you could have done it in a table. You could have your red, yellow, blue, and then you could have had long and short here. And then have it filled into the table like that. Red, long, red, short. Yellow, long, yellow, short. Blue, long, blue, short. Exactly the same in a table. I prefer tree diagrams, and the thing is, tree diagrams are much more helpful for the harder questions. Okay, so the probability that Joan wears shorts. Interesting. Okay, well the probability that Joan wears shorts, there's only long ones or short ones. So the probability she wears shorts is just a 1 in 2 chance. And the probability of her wearing blue and long, we say, okay, blue and long, I follow along that path, blue, long, multiply a third, multiply a half. So it's going to be, and I show this working every time, just in case you make a mistake with your fraction, you can still get the mark, 1 in 6. Now if that question here had, what if she had 2 red shirts, 1 yellow and 3 blue? All of a sudden, my probability, and I'll do this in a different color so you can see, all of a sudden this probability here would be 2 out of 6, this one would be 1 out of 6, and this one would be 3 out of 6. See how the probability changed if I mentioned different numbers? And if that was the case, then you wouldn't be able to do a table. Tables only work if each outcome has the same probability, which is why I much prefer trees, because they will work every time. Tables, not always. Okay, and that is the video for today. So what I want you to do now, have a go at the exercise. There's a few questions in this one. It's a bigger exercise. So these are the questions I want you to do, and all of the letters for me, please.